everyone, welcome. So since we've gone through the basics of mobile forensics, we're going to dive into a little bit more for the Android devices. We'll do the iOS a little bit later, but first we're going to focus on Android. So Android is a Linux-based mobile operating system that was developed for touchscreen mode devices. It was first developed by OHA, which is the Open Handset Alliance, which is a consortium of companies, Google being the primary contributor, of course, and commercial marketer. So first we're going to go through all about Android. So essentially what it's made up of. The Android forensic environment and tools that we'll be using, data acquisition, data analysis and recovery, and maybe some app analysis as well. So let's first talk about Android. So Android is a Linux-based mobile operating system that was developed for mobiles with touchscreen capabilities, again, developed by Open Handset Alliance, and Google is its main contributor and commercial marketer. So when you get an Android in your hands and you need to do an acquisition or any type of forensic investigation on it, you have to pay attention to the version that you're handling, as the evolution of each version will also come with new challenges. For example, the initial version of Android did not have full disk encryption, or FDE. So that's something that we have to keep in mind when we're handling these mobile devices. So with each new version, more security features were deployed, such as app permissions, trust execution environment, or TEE, and secure kernel. It's also super important to understand the basics of the Android architecture to ensure you have the basics of forensic concepts. Android releases its code under the Apache license, and it's an open source license as well, which means that anyone can access it, modify it, and use the software according to the requirements of any device. And each layer performs several operations that support specific operating system functions. So first we'll have the Linux kernel. That's the foundation of the Android platform. For example, the Android runtime, or ART, relies on the Linux kernel for underlying functions such as threading or low-level memory management. Using a Linux kernel allows Android to take advantage of security features and allows device manufacturers to develop hardware drivers for a well-known kernel. Some of these security features include an Android platform that takes advantage of user-based protections to identify and isolate app sources, so which is the Android sandbox. This isolates apps from each other and protects apps and the system from malicious apps. To do this, the Android assigns a unique user ID, or UID, to each Android application and runs it on its own process. Then we have the hardware abstraction layer, or HAL. This provides a standard interface that exposes the device hardware capabilities to the higher level of Java API framework. The HAL consists of multiple library modules, each of which implements an interface for a specific type of hardware components, such as the camera and the Bluetooth. When a framework API makes a call to access the device hardware, the Android system loads the library module for that hardware component. And like I mentioned, the Android runtime, for devices running Android 5.1 or higher, each app runs in its own process with its own instance of ART. ART is written to run multiple virtual machines on low memory devices by executing DEX files, which is a bytecode format designed specifically for the Android that's optimized for minimal memory footprint. Some of the major features of ART is ahead of time, or AOT, and just in time. JIT compilation, optimized garbage collection as well, and then just better debugging support includes a dedicated sampling profiler, detailed diagnostic exceptions, and crash reporting. Crash reporting is pretty handy in the forensic world sometimes if you want to know if somebody had used an application but had deleted the application and the crash report is still remaining. And then of course you have your native C, C++ libraries. I won't get too much into that, your Java API frameworks. This entire feature set of Android operating system is available to you through APIs written in the Java language. These APIs form the building blocks you need to create Android apps by simplifying the reuse of core modular system components and services. And then of course you have your system apps, which would be your dialer, email, calendar, camera, etc. So anything that the user has installed. Android comes with a set of core apps like your emails, your SMS messaging, internet browsing, contacts, and more. Apps included with the platform have no special status among the apps that the user chooses to install. So if a user installs an app for pet watching something, it doesn't take precedence over the calendar, and the calendar doesn't take precedence over what the user has installed. So a third-party app can become the user's default web browser, for example, or SMS Messenger, or the default keyboard, with some exceptions, of course, with the system's setting apps. And then the system apps function both as apps for users and provide key capabilities that developers can access from their own app. For example, if your app would like to deliver an SMS message and you don't need to build that functionality yourself, you can instead just invoke the SMS app that's already installed in the driver. It's already installed, sorry, on the phone to deliver a message to the recipient you specify. So we talked a little bit about security on here, but the foundation of the Android platform is the Linux kernel, of course. It has been a widespread use for years, and it's used in millions of security-sensitive environments, though its history is constantly being researched and attacked and fixed by thousands of developers because it is open source. Linux has become a very stable and secure kernel trusted by many corporations and security professionals throughout. As the base for a mobile computing environment, the Linux kernel provides Android with several key security features, which includes a user-based permission model, process isolation, extensible mechanisms to secure inter-process communication, or IPC. And then, of course, the ability to remove unnecessary and potentially insecure parts of the kernel. So if you have a multi-user operating system, a fundamental security objective of the Linux kernel is to isolate user resources from one another. So for example, it prevents user A from reading user B files, or ensures that the user A does not exhaust user B's memory or the CPU, or essentially other key parts of the device as well, such as the telephone, GPS, or Bluetooth. So Android has a file hierarchy. It's important folders are common for the most Android devices. We have the boot partition. This partition has the information files required for the device to boot. So it contains both the kernel and the RAM. Without this partition, the device would not start its process. And the system partition, this partition contains the system related files other than the kernel and the RAM. And then the recovery partition. This one is designed for backup purposes and allows the device to boot into recovery mode. The data partition contains the data of each application installed and used on the device, which is probably your most wanted partition. And then you have the cache. This partition is used to store frequently used or accessed data and some logs. So data and cache are probably your most wanted and focused partitions for an Android. It's also important as a forensic examiner to understand which file systems are being used and identify which ones are significant to the investigation. So the file system most important would be the one that stores the user data, of course. These file systems listed refer to the way data is stored, organized, and retrieved from a volume. Different partitions can be formatted and to use to different file systems. So flash memory, it can be erased and reprogrammed in blocks and retains data in the absence of power. And then pseudo files is just a logical grouping of files. So when conducting an investigation on a mobile device, it's important to maintain control of the forensic environment to prevent contaminations. And so the data needs to be protected at all times here. So when starting with a forensically sterile environment, it means that there's no other data present on the system or is set up in a manner that prevents any past investigations from contaminating the current investigation. Most Android forensic tools and methodologies will work on Windows, Linux, and Mac operating systems or platforms. And then you should have the ability to enable settings or bypass them in order for all workstations to extract the data from the Android devices. The Android Tools SDK, so the Android Software Development Kit, can help you extract data from the device by using the software libraries, the APIs, tools, emulators, and other material. There's a couple labs out there that will kind of guide you on how to use the SDK to extract from an Android mobile device, but I'll create one for you and put it in the contents and the resources so you can try it out yourself. So properly handling of an Android device is the same way that you would handle any other mobile device on site. So these steps can be mainly completed if the device is still active and is unlocked. Newer Android versions, should they have a screen lock or enable, won't allow you to place the phone on airplane mode without inputting a Touch ID or passcode pattern or Face ID. Due to the increasing usage of passcode options to lock Android devices, it's important to be aware of the screen lock bypassing techniques that are out there. So proper handling would be to place the device in airplane mode if you can, disable the Wi-Fi if you can, remove the SIM card if there's a slot, enable USB debugging, again, if you have that capability, enabling stay awake settings, again, and increase screen timeout. So all of these used to be super easy on the older Android phones. But these days, you need a lot of user permission. So those security features to be able to change any of these settings on a phone that you have access to. So for bypassing screen lock methods, there's a couple different methods that can be used. Some of these methods can alter the device, so you should only be performing them if you have proper authorization. Other methods listed may need the device to be rooted. We'll talk a little bit about what it means to root a device. A smudge attack is exactly what it sounds like. You look at the phone and you first you don't wipe it, but you look to see if there's a pattern that shows or where someone hits, and you can try to replicate that pattern on the phone to be able to get access to it. You can also use the forget password or pattern. This obviously will be linked to the, if someone has an account with Android or Google, it'll be linked to that account. So they would get a notification that you're trying to get in, and then booting it into safe mode. If there's a third-party lock, it might be easier to get around it. But other bypassing screen lock methods, I know Cellebrite has one, and then using my mobile, using Find My Mobile can also help you bypass the screen lock, but it's a Samsung only. So rooting means gaining root access to the Android device. So rooting access device to perform actions that are not normally performed or allowed on the device, so using administrative privileges. It allows for over and underclocking the device's CPU, if you're into that, and bypass carrier restrictions and download custom ROMs. But if it's not done properly, you can end up with a bricked phone. It does void the warranty, and then it also increases the risk of malware, mainly because you're removing that, you're kind of bypassing that Android sandbox that we talked about, where it kind of like puts a bubble around all your applications. So you'd be exposing your phone to some malicious malware. So data acquisition. Prior to extracting any data, as an examiner, you need to determine if root access is permitted, and then what data can be extracted during the investigation. You'll have a few options for data acquisition, so let's go over those really quick. There's 3 types of data extraction techniques. The first one is manual data extraction. There are some cons, which would be only files that are accessible via the operating system can be investigated. And then it's easy to press the wrong button and accidentally erase or add data if you don't know how to use the device. And it should only be really used as a last resort. So this means that you're manually handling the device to access and view information. So you're actually scrolling through the device. And then pictures can be taken of the evidence that you see on here. A lot of law enforcement uses the manual data extraction at the very beginning during a search warrant, because it's really easy for us to identify if that phone is worth seizing and taking with us, and kind of also identifying really quickly who owns that device. And you have the logical data extraction. So extraction of data by interacting with the operating system and accessing the file system. And then you can also root the device to grab additional data. So rooting a device can alter the device and should only be done with proper authority and someone who's trained to be able to do that. Root access is not typically required to obtain a logical acquisition. However, root access can influence the amount and kind of data that can be extracted. And there are several techniques to pull data. So you have an ADB pull or an ADB backup extraction or a dump-sys extraction. Or you can use, for logical data extraction, instead of using ADB, which is open source, you can use Cellebrite or Axiom. They both have capabilities. I think Cellebrite bought BlackBag, so they have iPhone capabilities, but for the Android, Axiom and Cellebrite are pretty good. There are other techniques, open source techniques, that we'll go over in a little bit. And then you have the physical data extraction, which is a bit by bit image of the device. Is the most common technique using the DD command. Other techniques are like JTAG and chip off, but this can damage the phone. Should only be performed by experts who have received training. There was a question that was brought up by my last video about mobile forensics, and the question was that the video talks a great deal about extracting data from a device's memory using different methods, but how about the RAM? Is there not a situation where maybe a malware or some covert app running behind the scenes might be an IOC? Yes. If that's so, how can the RAM data of a mobile device be extracted? So it was a great question. It kind of made me think a little bit and kind of go back on some of my some of the resources and the material that I usually give out to my students. But most of the phones don't allow you to access RAM or produce a true physical collection from the port. For a majority of commercial matters, the efforts it would take to do a chip off, JTAG, or a RAM chip imaging and interpretation are not worth the efforts, given the typical retention of data on the device and the data that is of interest. For example, In an iPhone, the majority of the relevant information is stored within SQLite DB or database, where records are deleted and reused. So if you perform a collection of the file system, that a database contains a large majority of that information and deleted records that you would be interested in. And most mobile devices require some sort of restart, which kind of clears a lot of the working memory. So, and typically the most important data is going to be in the SQLite databases. Celebrate does have a decent feature to help investigators parse the databases manually, because there's no way they can accurately parse every app in existence. So when it comes to deleted data, it depends on how the database were implemented. And some will retain a lot of deleted entries, but others will frequently clean them out. So it really depends on the application, how it's built. But on the collection side, most modern phones, such as iPhones and Galaxy class phones in particular, use newer and higher quality data storage, with actually encrypts data directly on the drive. There's no point in doing a chip off for these devices, because all you're going to get is encrypted data with no way to guess the key. So chip offs are reserved for older and cheaper model phones. And then the RAM capture, because a lot of phones require a reboot, essentially would just clear it out. But most of the applications use databases to store a lot of their information. So doing a logical data extraction would essentially just cover all of that. So data analysis and recovery. There are several tools that support the extraction and analysis data of an Android image. We have Autopsy, Celebrate, and Axiom. If you want an open source, there's also Lime, L-I-M-E, which stands for Linux Memory Extractor. This is the first tool to support full memory captures of Android smartphones. It does use ADB, so you do need to do the USB debugging on there. For Android devices, other than Autopsy, Celebrate, Axiom, you do have, if the user is using WhatsApp, there's a specific WhatsApp extraction. There's a tool called Scalpel, or SQ, and there's the SQLite browser as well that you can use, hex editor, to be able to parse out your hex dumps if you get to that. And then really anything that is capable of mounting an ext format, which FTK Imager does a really good job for that. And then we have recovery techniques. So when we're dealing with deleted data from external SD card, you can mount the card as an external storage device and acquire data using a tool that we previously discussed. If you're trying to recover deleted data from internal memory, you might want to do a logical acquisition of the device and then root the device and then do another acquisition. That data will have, you'll be able to extract not only the beginning, the before and the after, but also kind of see the differences in what a root device might look like, but also if you corrupt the phone after rooting it, at least you have, you know, a good version of the data before you rooted it. Of course, only root when you have permission to do it. And if this is the last resort, if you absolutely feel that there's data on that phone that can only be accessed after rooting a device, then that would be your reason. But otherwise, you don't need to root the device. You can just do logical. When you're going through the SQLite files, it's important to just check the unallocated and free blocks, because you might find some deleted files in there that are easily recoverable with some of the forensic tools that we discussed. And then, of course, use file carving techniques. So this recovers from the allocated space based on the file structure and the contents. I know that NK's Axiom and FTK Imager do that. I haven't tried it with Autopsy yet. and then use Google account for some data recovery. If you do have access to that Google account, or if you're able to either be granted access or permission to recover a data backup, essentially. And that's it for today. Next video, we're going to talk about the iOS and the security features on there, and the limitations of an iPhone as it keeps getting more and more secure for users. But there's still some things that can be done. So look out for that video, and I hope everybody has a great rest of your day. Thanks.